You step outside 100 billion years from now, and nearly every galaxy beyond our gravitational neighborhood may have faded beyond detection. At first, the sky does not look empty. Stars still form familiar patterns, and the surviving galactic island may look so rich that nothing seems missing. Then you aim a powerful telescope between those stars. Almost nothing answers. No broad population of distant galaxies. No clear recession pattern. No familiar background connecting the local sky to a hotter, denser beginning. The universe seems to have abandoned your island and taken its history with it. The obvious explanation sounds simple. Expanding space slowly pulled the stars away. Tiny problem. The stars your eyes separate into individual points were never the distant universe in the first place. So the real mission is to discover what expansion can actually remove. How a universe full of galaxies could become observationally empty, and whether a future civilization could prove that anything ever existed beyond its own neighborhood. To begin, we have to separate two skies that our eyes naturally blend together. The first is the sky we see without a telescope under clear, dark conditions. It contains only a few thousand individual stars, all belonging to the Milky Way, our own enormous stellar city. A few neighboring galaxies can also be visible without optical help, but they do not appear as separate stars. Andromeda, about 2.5 million light-years away, can show up as a faint patch under a truly dark sky. Its stars arrive together as one dim blur. The familiar constellations are not stars scattered across expanding intergalactic space. They are local lights, governed mainly by the Milky Way's gravity. Looking up with unaided eyes is like standing inside one city, seeing its streetlights, and assuming you are looking at a map of the whole planet. You are not. Expansion does not simply erase one star from Orion, then another from the Big Dipper. The ordinary stellar sky and the deep extragalactic sky are different layers. The first is local. The second is where expansion reveals itself. That distinction was not always obvious. In 1927, Georges Lemaitre published an expanding universe solution and connected it with galaxy observations. In 1929, Edwin Hubble published the distance recession relationship that became central to modern cosmology. On sufficiently large scales, more distant galaxies generally showed greater recession, but this is not every object flying away from one special point, or an explosion throwing galaxies through fixed emptiness. A better image is a flexible ribbon marked with widely separated points. Stretch the ribbon, and the space between distant marks increases. Now fasten a cluster of beads tightly to one section. The loose regions separate, but the bound beads remain together. The solar system, the Milky Way, and the local group are bound systems. Local forces and gravity dominate them, so they do not stretch with large-scale expansion while distant. Unbound regions separate. Light crossing that expanding distance is affected differently. Draw a wave on the ribbon and stretch it. The wave becomes longer. That is cosmological redshift. As light crosses expanding space, its wavelength stretches. Visible light from sufficiently distant galaxies can arrive shifted toward infrared and still longer wavelengths. Expansion, therefore, changes two things that matter to our future observer. It increases the separation between unbound regions, and it changes the light carrying information between them. For a while, that sounds manageable. Build better instruments. Observe longer wavelengths. Keep the cosmic inventory open. Then the story changes. Astronomers once expected gravity to slow expansion over time, rather like a car coasting uphill and gradually losing speed. But in 1998 and 1999, two teams studying distant Type 1a supernovae found that the late-time expansion was accelerating. The work was associated with teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, and was later recognized by the 2011 Nobel Prize in Physics. The universe was not merely continuing to expand, its late-time expansion was speeding up. The teams did not directly detect particles of dark energy. Their observations revealed acceleration whose physical cause remains unresolved. For our mission, the consequence matters more than the label. If acceleration continues indefinitely, sufficiently distant, unbound regions do more than move farther away. Light emitted sufficiently late in their histories never reaches us. Think of a video connection across a widening gap. The screen still shows the distant source, but the frames arrive increasingly stretched, dim, and delayed. Eventually, later frames do not arrive at all. The distant galaxy has not stopped existing. Its local time has not frozen. We have simply lost access to its continuing story. Now the future sky begins to make sense. But before everything beyond us fades, we have to identify what remains. The Milky Way belongs to the local group, which includes Andromeda, Triangulum, their satellites, and other nearby members. Gravity keeps this neighborhood associated while more distant. Unbound structures participate in expansion. Picture countless islands on an ocean widening between them. Islands strongly connected into one local group remain together. Other islands recede until no future message can cross the growing separation. Our gravitational island survives. The larger network disappears. Older descriptions imagined an inevitable Milky Way-Andromeda collision. A 2025 study, using Hubble and Gaia constraints, instead found roughly a 50-50 chance of collision within the next 10 billion years. They remain gravitationally associated, but the collision is not guaranteed. That changes the local details, not the larger story, whether they collide or remain separate. The local group can still become isolated from unbound galaxies. At this point, the opening premise has earned a real chance. The sky can remain full of local stars while the wider universe slips away. Under a standard projection in which dark energy behaves like a positive cosmological constant, galaxies beyond the local group scale could become effectively undetectable over roughly 100 billion years. Not on one dramatic night. Not at one synchronized instant. And not because the galaxies are destroyed. Their light becomes increasingly redshifted, their images grow fainter, the information arrives more slowly and represents earlier stages of their lives. The cosmic inventory does not switch from full to empty. It loses entries as each source becomes less useful to observation. A departing ship offers a rough comparison. It does not vanish because it stops existing. Its image becomes smaller, dimmer, and harder to distinguish until the horizon no longer delivers useful new information about it. For galaxies in an accelerating universe, we receive an increasingly limited image. While later light may never reach us, the future telescope may be powerful and its scientists brilliant. Their problem is not intelligence. The evidence is no longer arriving. That is the midpoint, where the story stops being about a sky losing lights. It becomes a story about the universe losing its witnesses. Local stars can still shine, and future astronomers can study planets. Gas, dust, gravity, and local motion. But the observations that tell us we belong to a much larger expanding universe begin to disappear. First, the distant galaxy population fades beyond practical detection. Then, the measurable Hubble flow vanishes from the observable neighborhood because the remaining visible objects are governed mainly by local gravitational dynamics. The astronomer sees no clear distance recession pattern. Nearby objects move under local gravity, not as part of a clean cosmic expansion. Evidence from the cosmic microwave background also weakens under the same long-term projection. That relic radiation becomes progressively cooler and more redshifted until it no longer functions as the clear, all-sky clue available to cosmology today. Stars also repeatedly process matter inside the surviving galaxy, complicating attempts to reconstruct the primordial origin of light elements. The room still exists. The event still happened. But the windows have been sealed, the old footage has decayed, and the footprints have been disturbed. In 2007, Lawrence Krauss and Robert Scherer examined this future and argued that observers could reasonably infer an old, isolated, apparently static island universe from the evidence available to them. They would not be foolish. They would be doing science correctly with a damaged archive. That possibility attacks a deep assumption any civilization in any era should be able to rediscover the same universe with enough intelligence and sensitive enough instruments. But observation depends on more than intelligence. It depends on timing. A civilization can inhabit the same universe and inherit far fewer clues. Reality may remain vast while its observable history contracts. That sounds like the final answer. It is not. The lonely future works only if dark energy keeps driving acceleration for tens of billions of years, roughly like a positive cosmological constant. That is the hidden condition beneath the entire projection. The observed expansion is real, the late-time acceleration is established, but the permanent long-term behavior of dark energy is not. DESI's first 3 years of data strengthened hints that dark energy may change over time, but this is not a settled discovery. DESI completed its planned observations in April 2026. The full survey is still being analyzed, with first 5-year dark energy results expected in 2027. So our future inventory screen must split in one branch. Dark energy remains approximately constant. Acceleration continues. Unbound galaxies become observationally inaccessible, and the local group becomes an isolated island beneath a sky that no longer reveals the wider cosmic structure. In other branches, dark energy behaves differently. We cannot fill those branches with confident endings. Evolving dark energy does not automatically mean a safer, collapsing, or non-accelerating future. The final chapters remain uncertain. We have projected the future using a rule that nature may not keep perfectly constant. Now return to the observer standing beneath that sky 100 billion years from now. The constellations may remain, with local stars filling the darkness. The surviving galactic island may look enormous and complete. But the telescope finds no clear external Hubble flow, no rich population of distant galaxies, and no familiar cosmological background tying local astronomy to the early universe. The observer asks the most reasonable question available. Is this island all that exists? The evidence around them may suggest yes. The history of the universe may say no. Cosmic expansion is not currently stealing ordinary stars from our naked eye sky. They belong to the bound Milky Way. Distant galaxies do participate in large-scale expansion, and their light stretches as it crosses expanding space. If dark energy remains approximately constant, nearly every unbound galaxy beyond our neighborhood could become effectively undetectable over roughly 100 billion years. Taking major evidence for expansion and the hot Big Bang from future observers, possible under the Standard Model, not guaranteed by the evidence we have today. And that brings us back to the present sky. The faint galaxies and cosmological signals available now are not permanent decorations. They are an archive, arriving while enough of the universe remains visible to reconstruct a history larger than our local island. We usually think ignorance begins when we fail to look. Sometimes it begins because we arrive after the clues are gone,